Everyone, and welcome back to our Activity 35 notes. Today we are going to talk about rotating and dilating with matrices. Our first part here with rotations involve us taking our column matrices that we talked about yesterday, representing our points, and multiplying them. So we have a general equation for a counterclockwise rotation. So that's cos of the angle that you're rotating by minus sine theta, cos theta. Or, which I think is the more important one, your clockwise rotation, which is cos theta, sine theta, negative sine theta, cos theta. Because what you can do is you can actually also rotate clockwise. Using this one, you would just plug in a negative theta as opposed to a positive version, and it would also, this formula suffice for a counter rotation. So for this first one, we have a rotation by 90 degrees clockwise. So we're going to take our rotational matrix, so cos 90, sine 90, negative sine 90, cos 90, and we are going to rotate our triangle ABC. So 1 over 2, 3 over 4, and then point C, 5 over 1. Now we can take our calculators and help us out with these rotational matrix. So if we type in, we're going to edit. Matrix 1 is a 2 by 2, and we can type in cos 90, sine 90, negative sine 90, and cos 90. And we will get our rotational matrix, and then matrix B, we can edit to be that 2 by 3 matrix are, so 1, 3, 5 for row 1, 2, 4, and 1 for the second. And if we multiply our two matrices A times matrix B, we have, we see that our rotated matrix is now going to have the coordinates of 2, negative 1, 4, negative 3, and 1, negative 5. We can also rotate by other. This time we're going 120 clockwise, so cos 120, sine 120, negative sine 120, cos 120. And again, we will be multiplying that by that same matrix, that same point. So this time, if we change this up, we can edit so that matrix A is now using cosine of 120, sine 120, cos 120, negative sine 120, and the last one's cos 120. And it'll store those for us, and then we can take matrix A times matrix B again to get our final value this time, which we will have to approximate. So if you scroll using the arrow, you'll see the rest of these just round to a couple of decimal places. So we have 1.23, negative 1.87, 1.96, negative 4.6, and then negative 1.63, negative 4.8. Now again, with the counterclockwise rotation, you can either use the rotational counterclockwise matrix, or we can use the same matrix that we've been doing. However, if you want to go counterclockwise, you can just plug in negative 55 as your theta value, and that will show the counterclockwise rotation. Again, without having to memorize a second matrix. So this time, if we enter in our matrix, again, and enter this in, so we have a 2 by 2, cos theta. Again, this time for theta, we're going to use the negative version of this since we are going counterclockwise. Sine, negative 55, negative sine, negative 55, and then cosine of negative 55. If we multiply this times our triangle, we see our new coordinates. Again, we might have to just round on these. since we're not going to have those exact values, scroll over. We have the approximation again of those coordinates, this time at negative 1.06, 1.97, negative 1.56, 4.75, and 2.05, 4.67. All right, now we can also use matrices to help us represent dilations. And notice if you are dilating, you could either distribute a scale factor or you would set up your matrix where that whatever your scale factor is going to be the k value for both the first and then that last entry. If you are only stretching horizontally, your k will be changing the first entry versus vertically we would change that second. So we can, again, stretch or shrink depending on the size of that scale factor. Now, the examples here, again, we're using our same ABC triangle. This time we want to dilate by a factor of 2. So when we dilate, everything ends up changing in our matrix, right? We end up changing both the x and the y coordinates both by 2. So this becomes 2, 6, 10 for the x's, and then 4, 8, 2 for the y's. If we are shrinking horizontally only, that means we are going to change our first value, but the last one will stay the same. And again, the reason being, when we are making our final product, we will end up changing each of the values of the x's are going to shrink by a half. So half of 1, half of 3, half of 5, but vertically there was no change. They all will stay 1 when that multiplication goes through. Last but not least, if we are stretching horizontally by a factor of 4, vertically, okay, what happens is we will have 4 for the first. The second part here, we are shrinking, so that'll be a vertical component. Again, we have our triangle, and as we multiply through the first row, everything is going to get multiplied by 4, but then we are shrinking by a quarter, multiplying through that quarter to get the y values. All right, thanks everyone for watching. We'll work more with these in class.